You got it. It's wonderful. Oh, you're so nice. Thank you. Okay, sorry about that to the listening audience and all the ships at sea. Yes, so do you see that how this thing works? How when a north pole suddenly appears here, the current that's generated creates a north pole due to the ring, and the ring's north pole is repelled by this thing stands north pole, and the thing shot up. And the bigger the current that you generate, the bigger the north pole is that's generated, the higher it jumps. And when we cool that copper ring down, we got it to jump very high because it produced a lot of current. So those are the cute tricks that one can play. More entertaining than, but you can use things like this for breaking things, in the sense of BRAK. If you have a moving metal moving through a magnetic field, you'll generate fields in the moving metal which will oppose the motion, so you can slow things down by passing the conductors. You can slow a conductor down by passing through a magnetic field. So that's the story there. It's really interesting that they're watching. It's great. Okay, so, oh yeah, well, so we do want to use, though, you see how handy that story would have been hard to analyze using the Lorentz force approach. It's a little easier to think of it in terms of changing flux. It's handy at times, and you can switch back and forth, and if you can use them, they will give the same answer because it's the same stuff. But we'll generally use the Faraday approach, the changing flux, and then we'll use Lenz's law to determine which way the generated current goes, because it'll always oppose the motion that's creating it, right? So you'll have various examples of Lenz's law, and we express the Faraday law as d flux dt, flux being the field times the area, and we started out actually with motional EMF, just because I think it's more continuous from the previous learning. And then we made the point that you can change the flux in different ways. Any way you change it, as long as it's changing, you'll generate an electromotive force. Now, the generator works by changing the angle of the loop within this, or you could turn the magnet with respect to fixed loops. But you're changing basically an angle. That's how much flux passes through the loop, is how the generator works. And I showed you the generator. It's in the book. Now, and you can also analyze the generator in terms of the induction by motion, by Lorentz's method. You can get the same answer, now thinking it as a V cross B effect. And I point out that basically the structure of a motor and a generator are basically structured. You just have a loop with a magnet. The difference is whether if you want a motor means the thing is going to generate motion. To generate motion, you got to put in current. You don't get motion for free. You put in current, you pay for it somehow. So to get a motor, you put in current, you get out motion. Because you put in current, the current then will be acted on by the magnetic field, and there'll be a force on the wires to make them turn, so you get motion out. Or if you put motion in by your force of your body, or however, put motion in, you get electricity out. But it's the same wire with this, and that's why they look alike. They are. And it was Faraday. In fact, Faraday, when electricity became known about 1820, he already made himself a little motor. He got things to move. And then he worked a little harder. It took about 10 years to figure out how to make a good generator. A funny story is that apparently some politician came into his lab and he saw this little motor going around, and he's working, generates a little bit of electricity, made a compass needle move, and he said, "What is this good for?" And Faraday supposedly said, "Sir, someday you will tax it." And he was right, as usual. Okay, then we saw this little power plant model. And you tried this thing. Then I tried to show you how just a simple idea of a changing magnetic, if you could get the nuclear dipoles, the hydrogen nucleus, to do a motion like this, and you put a coil over here, every time the nucleus moment turns around like that, it gets a DDT in the loop and generates a little electric current around the loop. And you take that out and you measure it, you can actually measure the fact that you're driving the nuclear moments, which is how you do magnetic resonance. This was Bloch's idea. He called it nuclear induction. That's the title of his paper, Nuclear Induction, how a nuclear moment can induce electrical fields in the wire. It's a beautiful paper. You should be able to read it, actually, because all of this is 8A and 8B. 8A is the change in angular momentum in a field, how a top wobbles. Why a top wobbles is that it's got angular momentum, but the Earth's gravity field is pulling it down. And if it has angular momentum, instead of just falling over, it falls, but it turns. The reason it's turning is if that top were an empty space, it would just sit like this. It wouldn't wobble. But the fact that the Earth is pulling it causes it to wobble. And it's that wobble that Bloch is using, the fact that it goes around like this, and he just puts a coil over here, and it's a pickup coil to pick up the changing magnetic flux. That's simple. That's why I say, when you do your exam, to look for the simplest, straight, basic idea. And you'll probably do very well. You may not win a Nobel Prize, but you'll pass the course, which is our goal here now. Unless you have ambitions to win a Nobel Prize, and all power to you, think of something smart. So this is the same idea. You have a top in a gravity field, and the top will just fall over, were not for the fact that it's spinning. And when it's spinning, it turns out if you look at the angular momentum and this and that, it'll wobble. And the same thing is going on when you put a nuclear magnet spinning in a magnetic field. It will wobble. And it's wobbling, you put the coil over here. And this, I think, comes from your book, as a matter of fact. It shows that if you have a sample in a magnetic field, if you can get the nuclei to wobble, if you have a pickup coil over here, I don't know which, this may be the pickup coil. I can't quite read it on this tiny screen here, but what you do is you just, you drive it with this coil, and that makes the nuclear moments wobble, and then you pick up the wobbly field with this one, and then you just amplify it. So that's actually in your book, page 684. I point out that at Harvard, they did it a different way, with a different electrical technique, but okay, there are different ways of looking at things. And the other way of changing the flux, B, since it's a product of the B and A, you can change the magnitude of B, which is what Bloch was doing. He was changing the magnitude of B that was going through the loop. Or you might think of it as changing the angle, but either way. But the other thing you can do is change the area. And you can do something like this. You could generate a voltage to pass through this resistor by pulling this rod. And that will change the area through which the flux is passing. And that will generate a current through the resistor. The price you pay is that it will be hard to pull this rod, because the currents that are generated are going to be acted on by this magnetic field and will oppose your pulling it. That's say. That's the way it works. Okay, now we did these eddy current things where a moving object passing through a magnet, or a magnet passing through near a metal, will generate opposing fields, and you'll get what they call eddy currents, eddy being kind of swirls of current, and will make things jump. I stumbled across this where some folks are using transcranial magnetic stimulation. I'm not sure exactly how this works, but they claim that they can bring magnetic coils, fluctuating fields, close to the skull and stimulate parts of the brain. I'm not exactly sure why that is. You know about it, by any chance?
Yeah, no, I don't know very much about it.
Well, is it generating an electric field, or is it the magnetic field directly? Do we know?
It's magnetic. It's similar to an MRI machine, but it's like portable.
Yeah, but yeah, it's supposed to affect your brain, like make you do things, right? It stimulates electrical activity. Oh, I see. Oh, that's good. I think that's very practical in some cases, where you can switch it on and shut people up. Wow. Yeah, but I'm just curious to know whether it's a magnetic effect, electric. Because if you have the BDT in the brain, in the head, the ions feel an electric field, and you get currents. So maybe the currents that are actually firing the neurons, because it's a voltage too.